We can make 3D models if we make. We can interpret it easier. It's easier to interpret it. And the simulation will be the real life conditions. But if you build a physical model, that will be more expensive than a 3D model. Plus, you can have a lot of element analysis experiments on it, like what kind of stress you have, deflection, thermal. All these can be done on 3D models. Plus, these can be directly used for manufacturing, that is CNCs or computer numerical control. Plus, you can also make presentations and market it. So, basic these 3D models, we have three basic types. One is wireframe modeling, the other is surface modeling, and the third is solid modeling. So wireframe modeling, basically, that's a line representation, not the actual model representation, but a line representation where you can see only the edges. You can't see any surface, you can't see any depth. You can just see the edges. So this is like thin wires it's constructed with, and you get the projected lines and curves. I'll show you again what is a wireframe model. Now this is a wireframe model. You can get the appearance, or you can visualize the appearance, but you can't see the surface. So this is the wireframe modeling, and the hidden lines are not removed. Now, what are the hidden lines? These are the lines here. The other side, if you see the port side hull, those lines can also be seen. So those are the hidden lines, which are not removed in wireframe modeling. In other modeling, like surface modeling, you can't see those hidden lines. But here in wireframe modeling, you can see the hidden lines, so they become more confusing. Now, I'll just again explain what is hidden line, because sometimes you get a question of what is hidden line. Suppose you have a DB structure or solid plate floor here, which you have in the DB, as you've done in second mates. Now, that was a girder. So that is not a hidden line because it's going fore and aft. It's not a hidden line. You can see it actually. But when you have these stiffeners here, I'll just make so dotted lines here. So these stiffeners are hidden lines because the stiffeners are on the other side. So these are hidden lines. These stiffeners are actually on the other side, not facing you. Now these are your manholes here. Then you have a lightning hole here. So these are the hidden lines. So in wireframe model, the hidden lines are not removed. But in the other frame modeling, the hidden lines are removed. So wireframe model is the simplest mathematical model. It is used for technique and commercial CAD/CAM systems. Plus, you can divide it into analytical and synthetic entities. This is a wireframe model. Now, the advantages of this wireframe model is that these are more effective, more quick to draw. You can have a multi-view drawing. You can have the lines as intersection of surfaces. So you can use it for finite element analysis. You can also input for CNC machines. And this becomes a basic for your surface modeling and solid modeling. Any higher order models are made from wireframe modeling. Plus, the storage of wireframe model capacity is less in memory, so it's very easy to store and display. But the disadvantages of wireframe modeling is these are just lines and curves. You can't see the surface. You can't define the volume, or you can't define the surface area. It is little difficult to interpret and visualize. Your hidden lines are there, which make it more complex and jumbled because they are not removed. Plus, you can't determine the surface faces of these intersecting models. You can't determine the faces here because these are just lines. Now we come to the surface model. I'll show you the surface model here. This is a surface model. You can't see any hidden lines here, so they are all removed. So you can just see the plane surface, but you can't get the depth of the surface. That is why you have a better model, which is solid modeling. This is surface modeling. Surface modeling, you define the surface areas, you get the edges of the object plus the surface. It's a mathematical function describing the path of the curve. And these are edited as single entities. And these represent the skin of the object, but will not give the thickness of the skin. You get the surface, but you don't get the depth. So the advantage is it eliminates the ambiguity which you had with the hidden lines, and the non-uniqueness, that is all eliminated. Plus the rendering is better. I'll explain after this solid frame modeling what is rendering. Is basically when you model have got a better visualization. You have the shading effect, so you get a better 3D model in that. You get a better presentation and make it more realistic. So the surface modeling is more realistic as compared to wireframe modeling. Plus you get a surface geometry for these machining, and you can also mold and do the die design with the surface modeling. It will also analyze your ship's hull or airplane fuselages or the car body with the surfaces. Plus, you can also show the roughness and color and reflectivity of the surface. But the disadvantage is you don't get the depth of the model. So you can't know what is inside the model. You can just get the surface. It's a complicated computation depending on number of surface, and it basically takes more memory than the wireframe model, the surface model. Now we come to the solid frame modeling. Is basically the 3D structure here with the thickness of the object you get. What is the thickness? What is the depth? All that you get with the solid frame modeling. So solid frame modeling is a representation of the solid parts of your object on your computer. The typical geometrical model is made up of wires that show your object in form of wires, but that can be 2D, 2.5D or 3D. Then you provide the surface, you get a surface model. When you get a solid model, then you get a realistic effect on your computer. You're getting a realistic effect, you can get the depth, you can get the volume of the object in 3D modeling, which is solid frame modeling. So this modeling can be used for CAD software, which you can see the designer, you can see the object from all angles, as like your real manufactured products. You can see from various angles, top view, side view, bottom view. And this helps the designer to be sure that object looks exactly as he wanted it. Plus, it'll give you additional vision. So any changes of flaw can be detected here, and that can be corrected. Now, disadvantages of solid modeling is difficult to construct, difficult to calculate mass property. More time is required for creation because it's a 3D model. The storage space requirement of solid modeling is much more as compared to wireframe or surface modeling. Thus, you have more time requirement for manipulation. So that is solid modeling. The last topic in this modeling, we'll have rendering. What is rendering? If you see this is also a model, a 3D model, but you have a better effect of your objects here. The depth of the picture you can know. The 3D effects you can get better with the light shading. That is all rendering. So the better the rendering, you have a software for rendering where you can get more realistic 3D modeling effect with the light color effect. You have more shading, more light effect, so you have a better depth appreciation of the object. So that is 3D rendering. Now 3D rendering is a 3D computer graphics process to convert your 3D model into 2D images on computer. So you have a photorealistic effect or non-photorealistic effect in this effect. So your simulation can be done of visual effects like lens flare, depth of object, motion blur, and these attempts to simulate visual phenomenon result from an optical characteristics of camera and human eye. So how the effect of realism is done with rendering. So these effects can lend an element of realism to the scene, and simulation basically is of camera effect, but it looks like it's real. So that is your 3D rendering. Just have a video of it. Good afternoon all. Continuing with your, we have one term known as nesting. Now I'll just show you with diagram what is plate nesting. अब suppose ये DB के टैंक का हमें एक सेक्शन बना, उसको मैं बेस्ट छोटा प्लेट, इसमें से बेस्ट अरेंजमेंट जिसमें कम से कम यूटिलाइजेशन हो, जैसे इसमें सिर्फ वेस्टेज ये वाला सेक्शन है, तो हम इसको लेके इसी तरह से हम कटिंग करेंगे। तो किस अरेंजमेंट में हमारी प्लेट की वेस्टेज कम से कम हो, दैट इज नेस्टिंग। तो नेस्टिंग refers to the process of laying out cutting pattern so as to minimize your raw material wastage. अब इसमें जो वेस्टेज होगी ओनली व्हेन यू आर कटिंग अ फ्लैट प्लेट, ये नहीं कि जॉइंट प्लेट को काट रहे हो फिर नहीं होगा, या कहीं क्लैंपिंग कर दी हो तब भी नेस्टिंग नहीं होगी। तो मिनिमाइज द अमाउंट ऑफ स्क्रैप रॉ मटेरियल प्रोड्यूस ड्यूरिंग कटिंग, यू हैव अ नेस्टिंग सॉफ्टवेयर। और इस सॉफ्टवेयर से आप एनालाइज करोगे कि आपकी शेप्स अगर प्रोड्यूस हो रही किस एल्गोरिथम के बेसिस पे, उनका किस डिजाइन में उनको रखोगे सो दैट आपका रॉ मटेरियल वेस्टेज इज रिड्यूस्ड। तो आप अकॉर्डिंगली नेस्टिंग सॉफ्टवेयर परचेज करोगे फॉर ऑप्टिमाइजेशन ऑफ योर शीट मेटल। तो व्हाइल सम केटर ओनली टू रेक्टेंगुलर नेस्टिंग, जैसे अभी हमने देखी तो वो रेक्टेंगुलर नेस्टिंग है, बट कई बार नेस्टिंग आपको चाहिए फॉर एनी ऑड शेप। तो दिस इज बेसिकली क्रिएटेड बाय कंप्यूटर एडेड डिजाइन टूल्स, डाटा को हम ऑटोमेटिकली। So here basically it verifies that the software is actually performing true profile nesting and not block nesting. Block nesting is an imaginary rectangle which is drawn around your shape and then rectangles are laid side by side. Profile nesting basically आपका odd shapes का है. So here you are reducing your wastage. So it also takes into account your limitations and features. Like machining cannot be done when your raw material is clamped into one place. Suppose your steel plate is clamped in one place, then you cannot do nesting and machining. Some machines can access only half the material at a particular time, and automatically it flips the sheet to allow your remaining half to be accessed. Then if you're doing a punching, then you have to see punching means making a hole. Then your width of the punch is to be considered. Now the shearing is permitted. Shearing means cutting. That is permitted only basis certain limitations of the machinery. Now this software takes into account the characteristics like you have got defects in the material, then you cannot take it for nesting. Then you have to discard it. Plus your quality should be uniform. Quality should not change. If your quality is not homogeneous, maybe it's thick in one area and thickened in less thick in the other area, then you cannot do nesting. Plus, if your direction constraints are there, if your fiber direction is changing, then also you cannot do. So basically, a computer aided design में काम आता है. This is one of the software which we use in shipbuilding. And the next topic, what we'll do is lofting and numerical control, and then we'll do modeling and rendering. So we done the lines plan. Now lines plan, अब सब lines plan को boards का ये process अब computer पे use करते थे, पे आ गया. Your curved lines are generated and used in plans for streamlined objects like your aircraft and boats, and the lines are made on your wood, and this you can cut and then join. So the technique can be simple as bending a flexible object as long as it doesn't pass over two non-linear points. So here you have a curved line, it's not linear, so non-linear points है, and then you have mathematical line tables जिससे आपको shape मिलेगी. So it is used in shipbuilding, where you draw and cut your pieces of hull and keel, and then you get a 3D design, and इससे आप ट्रांसफर करते हो बॉडी प्लान, हाफ ब्रेथ प्लान एंड शियर प्लान बनाया था लाइंस प्लान में, उसको फुल साइज प्लान में कैसे ट्रांसफर करें, दैट इज द एक्चुअल लॉफ्टिंग प्रोसेस. तो पहले वो रेड रोजन पेपर होता था जिसे मार्किंग करते थे प्लाईवुड शीट पे, और फिर उसके हिसाब से टेम्पलेट बना के फिर उसके एक्चुअल वुड से काटते थे बोर्ड्स का. नेक्स्ट प्रोसेस है आपका न्यूमेरिक मशीन कटिंग का. बेंडिंग होती है न्यूमेरिकल कंट्रोल, देन कंप्यूटर न्यूमेरिकल कंट्रोल मशीनिंग है which is used for producing your machine parts and product items. तो कई चीजों में लेथ मशीन आपके इंजनों में लगी है उसको भी हम CNC. So this is a specific CNC machine language, unlike our Java and all those things. आजकल तो आपका बहुत कुछ आ गया है जावा स्क्रिप्ट. So this allows your precision over your speed, location, coordination, feed rate, and this language enables precise control over coordination, feed rate, location, speed of your machines. Now इस machine से manual labor खत्म हो जाता है. So you can automate your job. A router or spindle can be used which resembles your drill bit, and accordingly you can cut. and the speed is more. Volumes can be generated without any errors, and you can customize your machines. What are your advantages of your CNC machines? Is your preciseness can be done. When your preciseness is done, you are eliminating human error. Number two is your endurance is very reliable because they don't stop, unlike humans, which want chai break all the time. Number three, production is more. Scalability is more. More designs can be made as per your specifications. Your scalability is more. That means more number of volumes can be created short time. It's got more capability, which your manual machines cannot do. So it can, once you feed your design, it can produce tremendously. Less labor is involved. The product is uniform. Unlike humans, if they cut, uniformity नहीं होगी. Cost is reduced. जबकि high cost है machine का, लेकिन because of scalability and volumes and high speed and specialization, your total costs are lower. Plus, you don't have any labor problems. So fewer headaches. Safety is better because humans are not involved. You can design retention is done because your software you can just feed in and save it in your pen drive. So you can retain it for other machines. Your maintenance cost is low because G-code machines are automatically updating themselves, and they are very versatile because they can make any component. What are the disadvantages of CNC machines? First thing is it's very expensive because the machine itself and the softwares and all are expensive. But if you go for long term, then your expenses are evened out because you have your client retaining and your reputation for quality and reliability. Now here your manual skills are obsolete because manual labor is reduced, and that creates unemployment. That was your lofting. Just see if we can see a video and then we'll go to modeling then. Anji, questions बताइए.
Ask any naval architect to explain how ships are designed, and they will most likely draw a spiral. The design spiral has been at the core of ship design for over 6 decades. So, how does it work? The design of the ship starts with a set of mission requirements and progresses through 4 phases: initial, contract, functional, and detail and production. Each phase runs through the same sequence of tasks. With each cycle of the spiral, the design is refined, the degree of complexity increases, and the number of design possibilities is reduced until the final design is achieved at the center of the spiral. In practice, however, the design spiral looks a bit like this.
The whole design is ready.
The resistance is too high. You need to redesign your hull.
Okay, how about now?
Okay, it's acceptable.
For you, maybe, but now the vessel is unstable.
And now?
Better.
Sure. I can't fit in 20 cabins anymore.
Okay, how about now?
We can only get to contract speed if we increase the power.
More power means a bigger engine. I need to resize the engine room.
We need more structural reinforcement. That's going to add weight.
The simulation results are out of sync with the design.
The stability is messed up again.
Fast forward a little, and this is how everyone starts feeling. Ship designers know that to remain competitive, they need to digitalize their current processes. As a result, they have invested into digital tools that aim to increase efficiency at each step of the design spiral. Those digital tools have yielded some noticeable improvement. However, this improvement has been limited. Why? Because the design spiral is not efficient. It is made up of separate steps, each focusing on one specific aspect of ship design and performance. By upgrading disparate manual processes to better performing niche digital tools, shipbuilders are perpetuating the collaboration bottlenecks and data silos in their workflows. What is needed is not a series of specialized design tools, but a fully integrated solution, from initial to detail and production design. To control the design spiral and minimize risks, shipbuilders need to bring all their multidiscipline design processes into a centralized environment. This will allow globally distributed teams to work with a common set of data, tools, and processes. The first step is to implement a comprehensive digital twin of the vessel to manage its mechanical, electrical, and software features in one single collaborative environment. Having a single source of truth will ensure that the various design teams and suppliers always have access to the most up-to-date design data. The second step is to adopt simulation-driven ship design. Deploying automated multi-domain design space exploration and optimization allows ship designers to understand, explore, optimize and test virtually every aspect of ship performance, from individual components to subsystems to the full ship system. Having confidence in the vessel performance from the earliest phases of design is critical to reduce development time and boost innovation. Finally, shipbuilders must implement a centralized system to manage life cycle and BOM requirements, traceability, weight, and configuration. They also need to adopt an integrated approach to engineering lifecycle management, with capabilities such as integrated requirements management and secure supplier collaboration. This will enable better process orchestration and further increase overall enterprise productivity. Today, ships are greener, smarter, more efficient, more versatile, and more high-tech than ever before. To manage this ever-increasing complexity,
Hi, welcome at Mastership tutorial videos. This time we are going to explain you something about nesting parts. So let's get started. Here we have AutoCAD with our Mastership installation. On the left side of our screen we have a set of plates, and on the right side we have a group of parts. And those are the parts we want to nest into the plates. All the parts, they already have their water lines, markings, inner contours, outer contours, and their ID block, so they are ready for nesting. So to do this, we go to the NC tab of Mastership. Here you can see all the NC related commands, and the first step will be to prepare the parts and the plates for nesting. So we go to prepare to nest. This command asks you to select all the parts and plates, so let's do that. And after confirming with enter, it will generate all the required nesting contours. Right, all the nesting contours are made, and the program asks if it can turn off the layers which will not be used anymore. Okay. So all we see now are the required nesting contours, so we can start with nesting. We have roughly two options. We have semi-automatic nesting and we have automatic nesting. In this case we will choose for automatic nesting because it's the most easy one. It has several options. You can nest all plates at the same time. You can nest one plate at a time, and we have specific options to do a quick nest or to nest the last plate, because in that case you want to have as much remnant plate as possible. In this case we will choose for one plate at a time. You will have to select all the plates and the parts and confirm with enter again. As you can see, the program starts with putting the small brackets and parts into the manholes of the bigger parts, and after that it will start with putting the parts inside the specific plates, and it will start with the biggest part in the corner and work its way to the center with the smaller parts until each plate is completely filled, and then it will continue with the next plate. Okay, now the nesting is done. We still see the nesting contours, so we can stop the nesting now, and then it will change back the layer contours to the normal situation, right? But as we see now, it still looks a bit crowded because of those ID blocks. So let's turn off those ID blocks. To the Home tab, turn off the part data and the part text layer, and to have the IDs nicely visible and that they are able to be printed on top of the plates, we have a specific command to do that. This command is also available in the NC tab, and it's create rebuild text. So when we select it, we have to select all the parts, and this way we press enter. And then we have several options. We only want to have the part text and the part IDs, or both. and both we choose for this case. Put part D ID text instead of part data blocks, yes, and also the production unit, no, that's not needed.
क्या आपको अपने बच्चों के लिए चाहिए एक परफेक्ट साथी? जीवनसाथी.com पर कुछ ही क्लिक्स में देखिए लाखों वेरीफाइड।
Welcome to the Orca Shop. I'm Rod. I am setting up a new playlist or series of videos on lofting out the set of plans that I developed for the 9-foot Ken Douglas rowboat that I own. So if you haven't watched that series of videos on my YouTube channel, you might want to just jump back and watch those. If you already know how to take lines, do you think you'll need for lofting? You're going to definitely need a nice good set of large calipers for just marking some points or measuring and copying distances. Some rulers. I've got a nice 48-inch straight edge here ruler. It's kind of nice and new, so you've got some plywood, but I'm going to actually just put some paper onto the plywood so I can take my lofting plans, roll them up and move them away if I need to. 18 would be this one here, so this would be station number 1. That's what that mark is right there. The other thing we measured, we know that the transom rate, we might just take these ones out and just kind of see where this wants to bounce to. It wants to just bounce for support. So as I draw, I'm not pushing. Measure distances to the profile of the outer stem. And so in continuing on with the outer rabbit line from the keel through, first draft of my body plan. And these curves are a little bit tight to be running a batten through in an S. So we're going to do our best to join up as many points as we can, and this is where the French curve starts to become your friend. So we can just kind of draw a line through here, then it kind of curves up in the other direction towards there, and we can just add in a body plan view and other views of the boat so that we have a true and corrected version of the table of offsets for the boat for future building.
So from the center line out, doesn't really have some dramatic changes in the hull shape. So that is a good talk to all of you again today. And today we are going to do a video on the interpretation of lines plans. Now, lines plans are things you've probably seen in books. Notably, if you've ever read like Anatomy of a Ship, you would probably have seen these things. And they're used to describe the shape of the hull. Now, a typical lines plan will have 3 different views. One of them is a profile view, which is looking at the ship from the side. Then you also have a plan view, which can also be called a half breadth view, which is looking from the top down. And you also have a section view, which can also be called a body plan view. And that's looking sort of at a ship from the front and the back. And with these 3 views, you should be able to take those, get a certain amount of measurements from them, and you would be able to essentially model the hull. So let's take a look at a real lines plan and see how everything works. So this is a lines plan for a 12-meter long trawler yacht. And I'm going to point out some key lines before I start so that you kind of have a reference where everything is going to be. So there'll typically be a baseline when you're looking at a profile view. You'll see the same baseline in the body plan view. And at the half breadth view, you'll see a center line. Right, so you got to try to imagine where these lines are when you're looking at a ship. If you're looking at it from the side, of course, the baseline's at the bottom. If you're looking at a sort of top down, the center line is going to be like right down the middle, right? And then of course, in the body plan view, you will see the baseline. And then of course, you will also see the center line. Now, these lines allow you to take measurements to all different points of where things are on the vessel in terms of the hull lines and things like that. So keep those in mind. Those are pretty important lines. Now, aside from that, you will also notice that in the profile view and the half breadth view, you will see the station lines, vertical station lines. And these station lines you'll see are generally numbered from 0 to something, right? And it could be in this case, because it's a small vessel, 0 to 10. In some large vessels, you can see, 0 to 20, maybe more than that. And depending on how intense the changes in certain parts of the hull, you might even see like half or quarter stations. So those vertical lines are also quite important. Now, in profile view, you also see these horizontal straight lines, and these horizontal straight lines are water lines. Now, of big importance is something called a WL, or design. This is where the vessel is expected to float at that water line when she is loaded as per standard and when she's in sort of calm water. So that's interesting. Like Honestly, it all adds up in a bit, right? And then, of course, when you're looking from, you've got the water lines, which are these ones here, these ones over here. Like, looked at this and you've noticed that, hey, wait a minute. In each of the views, there's also curved lines, right? Well, those curved lines are actually really cool. So let's look at the profile view first, and let me point. So you'll notice that in the profile view, you have the butterflies, and these butterflies are the ones that are curved, right? Because again, remember what the butterfly lines are, right? From down here, they are these nice straight lines. Picture in a second, a bit more. Here, you got sections coming out towards the side of the ship, and this gives you a sense how it was changing as you're coming out. At the sort of further aft you go in the ship, the changes much. And if you take a look at the picture, you get a sense of what this says. There was the buttock lines or curved lines. When you come to what you're seeing curved are the water lines. And again, this sort of shows you sort of what the shape of the hull is at what particular level that the water line is going to be at. Now, of course, I mentioned earlier the DWL very interested in, because this allows us to calculate a bunch of really important hull coefficients. So things like the water plane hull coefficient, this is where we're going to be calculating it. It's also very interesting to note, and this is something to pay attention to, that if you actually look at it carefully, you will notice that you'll notice that essentially what I've done is I've created an X and a Y axis, and then the water line basically, and I can sort of estimate that using something called rule or tractable rule. But that's also something similar, estimating the area underneath. Estimating an area, for example, is I would be able to calculate, sort of how big that area is. And if I compare that in relation to the length and the breadth of the ship, I would be able to get something called the water plane coefficient. And the water plane coefficient, along with a bunch of other coefficients like the block coefficient, things like that, would allow me to have a pretty good estimate with regards to things like the powering requirement or the resistance of the vessel. And to help you visualize what those water lines are, here's another picture. So the water lines are essentially cut horizontally across the hull, and you're getting sort of individual slices of the ship from top to bottom. Moving to the last bit, we have the body plan view. And in the body plan view, you'll notice that there is once again two straight lines, one of them being the water line, the other one being the buttock lines. And then you once again have one set of curved lines. Now these curved lines are the station lines that you saw in the hull view and the half breadth view. And this gives you a sense of sort of vertical sections of the ship and what the hull looks like. Then you have the left hand from the aft going forward. So in this particular case, 10 was the front of the ship. You'll see sort of 10, 8, 7. And you understand. One of the things you can do with it is you can make. This is actually one of classmates who was totally okay with using his model here to show you guys. So as you can see here, there's the half breadth view, right? And then there is the profile view. And then of course there you see the 2D body plan view. Once you've got all the 2D stuff done, well, then you can start to move everything into the correct three-dimensional space, right? So you can see where all the individual stations are. Well, remember, keep in mind that you have the dimensions for that when you were drawing the lines plans, right? So let's say you go from this body plan view, you take the individual stations, you move them back into the correct locations, right? Because again, you know that dimension. So you get everything laid out properly, and then you can use the lines that you have developed, right? And then you can develop them into actual surfaces, into solid surfaces. And this will allow you to get the shape of a hull. Now you'll notice that with a lot of the drawings, you'll notice that like there's only half of it, right? Well, remember the reason why. If you have half of it and most ships tend to be symmetrical, you can just duplicate it to the other side and then you'll have a complete hull. Anyways, in the case of this particular model, if you just keep working on other bits and pieces, like, the decks, the, other parts of the superstructure, so on and so forth, you can keep modeling it until you get to a finished product. But of course, when you're interpreting an actual just lines plan, you're mostly dealing with the hull, because that's what a lot of naval architecture is, right? Like examining the characteristics of the hull itself. Anyways, folks, I hope you enjoyed this video on interpreting lines plans and seeing sort of where it leads to at the end. If you had any comments or whatever, let me know in the comment section below. Aside from all that, take care. Have a good one. I'll talk to all of you again next time.
Writing's not that easy, but Grammarly can help.
Now, let's see some wireframe models example. Like here of one cube or one rectangular box available. Here of one diamond and here of one sphere available. We can easily see like using wires or electric cables, we can easily make this type of object. So this model is called as a wireframe models. Now here are one solid model example available. So in a solid model example, we can easily visualize, see like a actual model or actual object. Like here are one piston cylinder assembly available. We can easily see it display like a actual part or actual object, piston cylinder. And easily we can use this object for our engineering application, for experimental based or then how. Now let's see the difference between the wireframe models and the solid modeling. In a wireframe modeling, 2D entities like points, straight line and polygon circles are used to create a wireframe models. But where in solid models, the 3D entities like blocks, the cylinders, cones, sphere and torus are used to construct a solid model. Now, in a wireframe modeling, a wireframe is constructed out of wires. By using of wires, we can construct the wireframe modeling. Like here, we can easily see this wireframe model. So it can be easily made by using of wire. And in solid model, it appears like a real model. We can easily watch this and visualize a better for it is actually act like a real model. Now, in a wireframe model, it is incomplete and ambiguous, so it is confusing more, cannot clear our point of view. But the solid model is complete and clear, so we can easily visualize like it is act like a real and somehow it. And in a wireframe models, it cannot be converted into solid model directly. We cannot convert our wireframe models into solid models, but in the solid models, it can be converted into wireframe model by using our mouse. You can easily change a view of solid models into wireframe model. Now let's see a wireframe models. It is difficult to generate wireframe models for complicated parts. So there are we need to use some extra profile or curvature type of wire. So it is made difficult for us to construct a wireframe model. But in solid model, it is easy to generate the solid models of complicated parts in 3D. And the wireframe model, it cannot be used for the computer aided design and the computer aided manufacturing for our engineering application purpose. But in solid models, it can integrate and automate the design and the manufacturing. For our machining purpose in NC/CNC tool, our programming, we can easily use this type of model for our better viewment or better experiment. Like in wireframe model, it requires less computer memory for working and the store. But in solid model, it requires more computer memory as well as storing. Because in solid models there are geometric entities available, and also there with topological entities also available or information available, which take more time compared to the wireframe model. In wireframe model, we cannot calculate the mass and volume, this type of data. But in solid models, we can calculate the mass and volume type of data.
Baby, if I give you 1 crore rupees, lots of money, what will you do with that?
Hello friends, in this second part of geometrical modeling lecture, we'll see modeling. We have discussed about wireframe. Okay, now we'll see what is surface modeling. Then again solid. Fine. Now surface modeling, as I said, it is wireframe becomes the base for this particular surface modeling. Okay, in surface modeling there are many types. For example, if I consider a box of this kind, now this box has been developed by using different surfaces. maybe S1, S2, S3, S4, S5, S6. So to develop a box, I need to have 6 surfaces. Whereas in the earlier case of if you consider a wireframe model, you have to consider V1, V2, V3, V4, V5, V6, V7, V8. Okay, so you have to consider 8 vertices or vertex. Okay, to develop a wireframe model. Hey, this is the case. Okay, now 6 surfaces are required to develop a surface model. Again, this is also not a complete representation. Here there might be few problems, but this type of modeling is also required in case of automobile or aerospace engineering. The application point, if you'll talk about a surface modeling, we can call it a sheet metal work also, is aerospace industry and automobile industry basically. Okay, other than this there are many other ways, in core industry, like to develop a boiler. In many other cases also surface modeling will help. Okay, now this surface modeling is of many types. Okay,
so next class I'll be doing all modeling, so that's why I was showing you the videos. So we'll do modeling in the next class, and after that we'll be doing past papers, and after that we'll keep continuing, right? We'll have a break now.